Yeah, it seems like when you complain a little bit, Mother Nature listens. Yesterday I was complaining about the lack of weather, and now we've got the fire hose of tropical moisture flowing northward. And that is certainly visible on the surface map. You can see those 60s dew points flowing out of the Gulf into eastern Texas and up to Oklahoma. And with it, the blue station plots indicating marginal VFR conditions, and we've even got some IFR from Lufkin, Shreveport up to Little Rock. There's a look at the southern plains using minimal smoothing on the isobars. There's that front coming down just northwest of Oklahoma City, all the way down towards the Hobbs area. The dry line is pretty far west, and it's not all that strong. We've got mid-50s on one side and 30s and 40s on the other. The moisture axis, that is going to be located roughly about right here. Maybe a secondary one further out towards Texarkana and Shreveport. And that's probably going to correspond to some of the deepest tropical air. And we do want to be concerned about that with a cold front coming south, impinging on that tropical air. That can sometimes be a recipe for convection. Here's a look at the high-resolution rapid refresh. The moisture axis, yeah, that corresponds to what we see on that surface plot. Let's take a few readings. Let's try around McAllister, Oklahoma. What is the quality and depth of that moisture? It actually doesn't look too bad. That looks like maybe 120 millibars of moisture. That would be adequate to support convection. There's only a very small tapering off from 61 to maybe 57 degree dew points up at about 1 kilometer. But the problem looks like it's going to be this cap, very strong cap there, lots of convective inhibition. And the convective inhibition values run from about minus 150 up to minus 300. How does it look further south? Let's try around Corsicana. The moisture looks a little bit more shallow. There's more dry air above that layer, and looks like the cap might be a little bit deeper. Cap strengths, yeah, those are pretty similar there. Now, another factor that we want to look at is about roughly the layer the cap is at. That appears to be about 700 there near the Red River. That's going to be around 750. So it can be helpful to go up to 700 millibars and look at the temperatures. That'll give you some indication of the cap strength. It looks like it is stronger down in the area south of I-20 and probably weaker near the Red River. And we also want to know the trend in temperatures during the afternoon. Let's run that forward from 12Z up to 0Z. And there we go. Looks like a very slight cooling, but I would say overall not much change at all. Then by evening around the Red River, we do have a loaded gun sounding, but it looks like that cap is still in place and there's just not much cool air in the mid-levels. We want to see the lapse rates kind of steep with that red line leaning way over to the left, and we don't have that. I would also like to see that cap just a little bit lower. And then a look at the mesoscale models. We'll just take a quick peek to see if we break out any convection. Nope, not really. The stuff you see here is forced descent over the front. That's not going to really do much. And we'll take a look at the WRF ARW. And that's not breaking out anything either. That's going to be a dry front. And SPC looking for nothing at all. Well, I've got to say the moisture return actually looks pretty decent, but I do see on the western periphery, it looks like it's already burning off. We'll just take a quick check of where the front is. Yeah, it's pretty much still northwest of Oklahoma City. So what we see here, this is probably just some sort of gravity wave feature. Now, one of the things we look for on the satellite is moisture erosion, especially on the western periphery of the moisture axis. Now, if there's moisture erosion where we have cumulus and stratocumulus vanishing during the midday hours, that tells us that the moisture supply is weak or that there's dry air being mixed down to the surface. But we do know from looking at the skew-t's that it is the cap that is going to be the main problem. And elsewhere, we've got that old receding polar high sitting off the Carolinas coast with another cold front coming through the Great Lakes. Driving that cold front, this 1032 to 1036 millibar high across the Dakotas into Idaho. Now, most likely the eastern part of this is of Canadian origin, and the western part is of Pacific origin, though it's kind of stagnant. It represents high pressure that's moved into the area and is now just kind of sitting there. And just a quick peek up there in northern Canada. Doesn't look like much polar air on tap. There's a little localized cluster of Arctic air sitting in Yukon, far eastern Alaska, but I don't think that's really going anywhere. The central pressure is 1032, and we really want to see that up near 1050 to 1060 before that's going to make a move southward. Even 1040 would be good, but we don't have anything like that. And you can see the temperatures on the southeastern periphery, minus 13 at Fort Nelson. That's not really cold. And they've got a south wind, so I don't think any of that polar air is coming down south just yet. And then a check of the upper level conditions. This is 250 millibars up at the top of the troposphere showing the jet stream activity. We've got a zonal pattern in place. This is going to favor a lee side trough in Wyoming or Colorado. There's the jet axis right there. And then we have this new feature coming in, very strong jet stream south of the Aleutians with a very deep trough. Also got another trough right there. Let's see what happens to this mess going into next week. Looks like that digs onto the west coast right around Sunday. There's the time right there, the date, in case you want to track that. And let's roll that forward. Looks like a very cold, stormy pattern for Monday, and then rapidly improving on the west coast. But all the action moves into the Rockies around Tuesday. What we've got here is a kind of a short wavelength pattern. We've got one trough there, another trough here, and another trough out there. So we're going to have some fast changes through much of next week as these ridges and troughs work their way from west to east. Then it looks like around Friday, Saturday, another outbreak of cold air on its way south. This indicates the fronts doing roughly like that, and another burst of cold air coming south for next weekend. Then it looks like it gets even colder, some more cold air coming south. You can see this little vortex developing over the Great Lakes on the 30th. This is a good 120 knot jet, and that's going to kick even more cold air southward around the 3rd or 4th. And with this very deep trough there, this looks to be involving some tropical moisture, so I think we're going to be seeing some severe weather in the southern U.S. around that time. And then going up to the end of the run, it looks cold again. Wow, this is a very typical pattern we see during severe cold waves. Now, this is 366 hours out. GFS does have a cold bias, but that'll be something that we certainly need to watch. So we're talking about December 5th, first or second week of December. And now for our dynamics lesson. Yesterday we talked about deformation zones and how they interact with thermal boundaries to allow for frontogenesis or frontolysis. Let's take a look at today's map. Where do you think the front is? This is isobars and thickness. Well, if we look at the thickness, we do see a ribbon here. This is obviously some sort of transition zone, and it looks like it might extend all the way out into California. We do find the southern end of that transition zone seems to kind of coincide with these troughs here. So let's put it together. Now already I can see that the surface map that we opened with is missing some detail in the western U.S. portion. We did have a front in that area, and you can see the strong pressure gradient there in Nevada. But anyway, yeah, the front goes from the Great Lakes down to Oklahoma and then over to northern Arizona and the Mojave Desert. So what kind of factors may be strengthening or weakening this long ribbon of a front across the U.S.? Well, one factor might be the interaction with divergence and convergence in the upper levels. Let's take a look up there. And so what do we see here? Well, most of the vorticity is channeled. We don't see much crossing of the height contours. This is 500 millibars. We're up at about 3 kilometers. It's formed up into a series of channels, and that tells us that the dominant process is jet streaks and the motion associated with those fields. Looks like there's a jet max right there over northern Michigan. That places the jet axis like that, and strong cyclonic vorticity up north, and you see all those orange colors. And then south of there, negative vorticity. We don't have a good scale for that. This particular site does not really convey the negative vorticity values well, but they are on that south side of that jet streak. So what do we see here? Yeah, there is some positive vorticity advection right up there. In that zone, low vorticity is being replaced with higher vorticity coming in from the west. So we would expect upward motion there. Well, here's a different pattern. This is 48 hours from now. This shows a strong shortwave trough moving across Minnesota and Iowa. With that, we have a vertical motion field, upward motion ahead of it, and sinking motion behind it. So if we have this rising motion ahead of the shortwave, how is that going to interact with any fronts down in that area? Well, upward motion is going to result in convergence in the low levels, and convergence will help tighten up the temperature contrasts. So this is going to be favorable for frontogenesis right there. This area behind the shortwave, favorable for frontolysis. Where are the fronts? Looks like they're pretty well to the south there. So that's going to be Paducah, cold front down to DFW, warm front over to Washington, D.C. So as this area of PVA, positive vorticity advection, approaches the front down to the south, or at least grazes it, we would expect frontogenesis down there. So likely that weather system down there will not weaken. Low-level convergence, that always supports frontogenesis, but it doesn't necessarily guarantee it. These upper-level dynamics are actually critical. Positive vorticity advection is a diagnostic tool for divergence aloft, and the associated low-level convergence will support frontogenesis. And cyclonically curved flow in the boundary layer also is associated with low-level convergence. Well, we've got cyclonically curved flow all around that low, so that kind of goes to show you that low-pressure systems do tend to support frontogenesis by their very nature. You get that convergence along the troughs, and you get the thermal gradients increasing. And likewise, negative vorticity advection, anticyclonic vorticity advection, like you would get on the backside of a shortwave trough, that's going to be associated with convergence aloft, and that will tend to spread apart your thermal contrasts underneath and lead to frontolysis. And that'll wrap up another episode of Forecast Lab. I appreciate you all joining. We'll see you on Monday for the supporters, and the rest of you on Tuesday. Have a good one. Bye-bye.